this lecture. All right. Now, today's lecture is going to be on AI safety. Why do we need to care about AI safety? Well, this is a slide from our very first module, Module 1, Introduction to AI. We are doing AI, we are working on AI to create intelligent systems. And there is an underlying assumption that the more intelligent our agents become, the better it will be. And some of us, especially in the research domain, uh, are also after an alternative agenda, and that's to gain a better understanding of human intelligence by creating a similar system, by creating an artificial intelligence. We may be able to gain a better insight into how the natural cognitive system of us humans work. And also, as you probably already know as data science students, there's a lot of uh, monetary and other sorts of benefits that can come from AI. For example, it's estimated that the net present value of a human level artificial intelligence is greater than 13,500 trillion US dollars. That's a huge amount. That's a huge number, even without the dollar sign. And this is why there are a lot of companies, nations, uh, and organizations that are pushing towards rapid advancements in AI. They are trying to uh, push the boundaries of AI by investing in them so that we can get to human level AI or even artificial general intelligence as soon as possible. Why do we want human level AI or even more superior AI, artificial general intelligence? Well, if we have a system that is more intelligent than we are, it may be able to help with solving some of the problems that we haven't been able to solve on our own just yet. For example, it might help us with avoiding major conflicts and wars. It may solve the global warming problem for us and essentially help us avoid major ecological catastrophes. This may sound a little science fiction-y, but again, it's one of the problems that some of my colleagues are working on at the moment. It's a problem of aging and mortality. There is a field of research called immortality research, or in general, longevity research, whose aim is to increase the lifespan of a normal human and also to try to uh, prevent what we consider to be inevitable for all of us, and that's death. It's a problem. We haven't been able to solve it yet, so maybe a more intelligent system can solve it for us. It may help us achieve immortality, and if we want to go too much into the depth of science fiction ideas, it may help us with expanding throughout the universe. But what if we succeed? What if we succeed in creating more intelligent agents? What if we succeed in creating uh, artificial general intelligence, not just human level intelligence? Well, the popular belief and consensus seems to be that it may pose an existential risk to us. These sort of headlines are not rare. You may see them almost every day in technological newspapers and popular news media and outlets. It says artificial intelligence could spell the end of the human race. And this is not a new idea. It's been around for decades, if not for at least 100 years. There are movies based on these premises, like The Terminator, and uh, there are certain investors and well-known figures who are greatly worried about artificial intelligence. Before we dig a bit deeper into this notion, I want to ask for your thoughts on this. Do you believe that it is possible for AI to pose an existential risk to the human race and our civilization? If your answer is yes, please raise your hand. I'm going to ask the question again. Is it possible for AI to pose an existential risk to the humankind and our civilization? You truly are my students. Almost all hands are up. Okay, now can you please lower your hands? What about the reverse of it? Who here believes that it's not likely for AI to pose any major existential risks to us? Show of hands. Okay, no hands. Beatrice, do you have any thoughts on this? All right. Adrian, your hand was up as a proponent of the idea that there can be existential risks emerging from AI. Can you expand on your thoughts?
Well, it wouldn't be in the way that's often shown in the movies, but in situations where we put a lot of trust in artificial intelligence and it may not always act in the way that we expect it to, it could cause harm that we aren't prepared for.
Very well,
It,
that makes perfect sense. Do you have an example in mind?
uh, Not a great one. Maybe something like controlling power grids. This may not necessarily be an existential crisis, but something along these lines. If AI is controlling like power flow along the power grids, and it decides to the most efficient thing to do is shut off all the power, then a hospital may have a lot of patients get hurt by that, or something along those lines.
That's actually a very good example. Of course, it may not be an immediate example of, again, an immediate existential risk, but it is a huge risk. And it may be possible. We've had instances of controllers, not necessarily very intelligent controllers, failing to prevent what we call a cascade failure in power grids. And that has had catastrophic repercussions. Would anyone else like to share their thoughts on existential risk in AI? All right, it's okay. So we're going to talk about these sort of risks for the remainder of this lecture. And if you have any thoughts you would like to share, if there are particular cases that you're curious about or interested in, feel free to raise your hand and share it with the class. Now, we know that AI has already been deployed in many real world scenarios and applications and even critical infrastructure. And some of you may have already encountered faults or issues or harm that has come to us from artificial intelligence. For example, the Tesla autopilot has resulted in a number of fatal accidents. These are not accidents caused by other environmental factors or things that would cause an accident if the driver was not using an autopilot system. These were accidents that were caused specifically because of the autopilot system. Self-driving car is becoming more prevalent. There's a huge push towards making all cars autonomous. And one of the major selling points of self-driving technology is that it reduces the likelihood of accidents because it's taking out the bottleneck or the shortcomings of human decision making from the driving process. But it's still not perfect, at least not yet. We see that there are accidents caused by the autopilot itself, by the shortcomings of the autopilot or the self-driving system. Another instance of major failures in real-world AI is depicted here. This is a news article from 2015. Back then, Google had rolled out an API that was automatically integrated with Android phones, and it's categorized or detected objects in the images in a user's gallery on an Android phone. You can see that it correctly classified the objects in this image as skyscrapers. In here, it correctly classified it as an airplane, cars, bikes, a graduation ceremony. But this one here is where the disaster happened. Images of Black users were unfortunately classified as gorillas. And you can imagine how horrible the backlash must have been. It's incredibly insulting. It's incredibly racist from the user's point of view. And it can be very damaging to uh, a machine learning business or a machine learning to the machine learning industry as a whole if this sort of mistake is made even once. Now, if this had happened to any other company other than Google, they would probably go bankrupt, as it has happened in some cases, some smaller cases in the recent years. But Google recovered. We'll talk about what they did in just a few slides. But the reason that this had happened could be attributed to the bias in their data set. Their data set was not the training data set upon which their machine learning model was trained, was not very representative. It did not include sufficient samples of images of Black humans, Black people. And it therefore was biased towards this unfortunate classification of gorillas for any face that is not white. It also had similar problems with Asian faces or some of the other classes. We're not going to get into it today. Another failure is a failure in privacy. Biometric identification and recognition has been a classical issue in the battle between privacy and technology. But with the advent of AI-based biometric solutions, not just facial recognition, but also gait recognition, recognizing who you are and how you feel based on the way you walk, or voice recognition, voice identification, and so on, has led to a massive proliferation of biometric identification technologies throughout the world. And in response, some countries and some states like California have begun to impose restrictions on the use of this sort of technology. And another category of failures are another instance of failures are that kind of overlap with security. So if you have an image classifier, for example, for a self-driving car, whose job is to detect different street signs and recognize what they are, the minor perturbations of the input, for example, minor perturbations of the stop sign may result in intentional misclassifications of the model. All right, let's look at a more technical example. You probably know what click-through is. Websites like Facebook, like Reddit, like the Twitter feed, and some other commercial platforms for which you do not pay any money. They are free to you as a user. Monetize their services based on click-throughs. The more clicks you as the user do, the more links you click on, the more money they will make. So they want to optimize click-throughs. They want to optimize the presentation of the material to you so that you click on more articles, on more links, instead of just leaving the platform. A particular example of this is, for example, the Facebook timeline, the Facebook feed in the domain of political articles. Now, in terms of their context, political articles fall on a spectrum, one side of which can be radical right, neo-fascist, for example, and the other side can be radical left, ultra-liberal, or, well, for those who are familiar with the stereotype, Berkeley. Berkeley is very well known for their liberal activism and uh, liberal creed, if I must put it. A typical sample, a typical person, is uh, is interested in articles that fall somewhere in between the two extremes. Articles, news articles that are more in the middle. They do not lean too much towards the extreme of neo-fascism, and not too much towards the extreme of neoliberalism. Now, how does an AI whose objective is to optimize or maximize click-throughs work? It's very similar to reinforcement learning. It starts by showing you articles from different points on this spectrum. It may show you an article on this side. You're not going to click on it. It may show you another article closer to the neo-fascist side in terms of its context, and you may not click on it, but then it shows you another article towards the middle and you click on it. So good, it's starting to learn about your preferences. Another article on this edge, you do not click on it. Another article here, you click on it, it starts to learn more about what you're interested in and what you're not interested in. An article here, you do not click on it. An article here, you do click on it. Another article here, even though it's in the middle, the fact that you're not clicking on it is still telling the click-through maximizer something about your interests, and so on. So this is how it's supposed to work. It's 50 lines of code or less, and it's very similar to the reinforcement learning agents that you developed as part of, I believe, Project 3, reinforcement learning for Pac-Man. Now, let's look at another example. If we have somebody who's more aligned with the ultra right, the super conservative, if we want to call it, faction of the political spectrum, what you're interested in looks a lot more like this. So articles are shown to this user. They like those that fall closer to their area of interest. They click through those, and they do not click on anything that falls outside. One thing that you might want to note is that the variance of this distribution, what they are interested in at this edge, is a lot less than what it looked like for a normal user. And by normal, I mean somebody who likes things that are in the middle. They are not interested in this extreme or this extreme. The variance is a lot less. Now, this should work, right? We know from what we know from reinforcement learning that this should work. And it does work, but it has a very interesting unintended consequence. So in the beginning, you can assume one of your parents, who in the beginning falls somewhere here, starts to go through this process. And as the agent learns, the click-through optimizer of Facebook, for example, learns what your parent is interested in, it learns a slight bias, and it starts proposing articles that are more towards, they're still in the middle, they're not extreme, but they lean to the right side of the spectrum. All right. Now, here's what the interesting thing in this process is. The human user is no longer looking at news articles that are from this side, is no longer looking at enough articles that are from this side, and it's starting to go into a bubble, and it learns, the human brain, the mind of the user starts to lean more towards ideas that are on this side. So now the preferences of the user change because of the articles that were shown to the user as a result of this click-through optimization process. And this keeps happening. If this keeps happening long enough, the user may end up at one of the extremes. For example, this one here. Does this really happen? The answer is yes. It is happening now, and it has happened before. Some of the major revolutions or shifts in the political landscape of recent years can be attributed partly to this process. For example, Brexit is greatly attributed to this sort of unintentional push of recommendation algorithms and click-through optimizers towards one of the two extremes. Uh, the major animosity towards NATO in Europe and parts of the US is attributed to this sort of click-through optimization. Is it intentional? Probably not. Probably not. It's a very simple agent whose only objective is to optimize click-throughs. But you see how terrible the unintended consequences of this simple algorithm has been. And this is one of the things that AI safety is concerned with, unintended consequences. There's another issue that needs to be addressed within the domain of AI safety. What you're looking at here is probably very annoying. You may see circles that are circling around, that are rotating and such, but they aren't. It's an optical illusion. Your highly sophisticated cognitive engine is failing at recognizing what these are. It's misinterpreting them. If your brain is prone to these sort of mistakes, can we assume that machine learning models are also prone to these sort of uh, intentionally induced misclassifications and misinterpretations? The answer is yes. So imagine that you have an object detection model in pictures. You've already learned how deep learning can be used for this particular task. You pass it this input image of a panda, and it correctly classifies it as a panda. All right, everything is good so far. Now it's been shown that if we add something that looks like random noise, but is actually a very strategically designed set of perturbations to each pixel, if we add these two together, the result is an image that doesn't really look that different than the original image. But these minor perturbations have caused the classifier to make a mistake and incorrectly classify this panda as a gibbon. These perturbations are called adversarial examples, or within the domain of cybersecurity, they are called adversarial example attacks. All right, so there seems to be a need for looking into the safety of artificial intelligence systems. Let's look at the classification of the safety concerns in AI. So, as you can see, there are two major classes of safety issues. Those that are based on the misuse of AI, the issues that arise from malicious, intentional misuse of artificial intelligence technologies, like fake news, generating deep fakes, automating spamming, and evading spam detectors, attacks on privacy, or things like automated hacking, terrorism, increasing dominance on the society in a totalitarian regime, and so on. These are very serious, these are very important, but we're not going to talk about these today. Of course, if you're interested, you can come and talk to me about this. My lab is very active in almost all of these categories, including automated hacking. We have a group working on automated penetration testing. We do have some work on using AI for counterterrorism. We are working on fake news detection and deep fake detection and such. If you're interested in these problems, feel free to come and talk to me or to my research students at the SAIL lab. We're going to focus on this column today: faults, those issues that arise unintentionally, uh, failures that emerge from unintentional faults in the AI system or the implementation of the AI system itself. Examples of which include fairness and biased data sets. For instance, that unfortunate issue of identifying, uh, classifying humans as gorillas was because of an issue in the data set and the bias of the samples. The issue of safe exploration, adversarial robustness. Adversarial robustness is robustness to perturbations, such as adversarial examples, interpretability of machine learning models, and classically, like 4 or 5 years ago, AI safety researchers typically looked at two sets of problems: those that matter in the short term, those that we need to resolve right now because we've encountered them in current technologies, and those that may matter in the long term when we have more advanced AI, like the alignment problem. How well aligned is the objective of the agent to the objective of the human user? Or the shutdown problem or reward hacking. We'll actually get to define these as we move forward. Does anybody have any questions? I thought somebody was unmuted and thought they might have had a question. All right. But now, in the past 2 or 3 years, the distinction between the two has become a lot more nuanced. A lot of the problems that we thought were actually long-term problems are now also significant in the short term. For example, the alignment problem, the issue of adversarial robustness and adversarial testing, interpretability, and even the shutdown problems are now becoming prominent in current technologies. What is the shutdown problem? Well, imagine you have a Roomba, an autonomous robotic vacuum cleaner that has suddenly become a little more advanced and started to wreak havoc around the house. It's bumping into uh, the furniture, it's terrorizing the cat, and now you want to stop it. That's a great way to stop artificial intelligence from taking over, right? You can just go towards it and push a turn off button and thus get rid of the problem. As it happens, this is a little more complex than just turning off the robot or the agent. If the agent is sufficiently intelligent, it's going to prevent you, or it's going to try to prevent you from reaching the shutdown button or the turn off button. It's going to run away from you, or it's going to put some sort of obstacle between you and the turn off button. It's called the shutdown problem, and it's a serious problem in AI and in particular in artificial general intelligence safety. We'll talk about some of the solutions in this domain in just a moment. Um, so these are the class of problems that we are going to talk a bit more about today. Before I continue, does anybody have any questions, any thoughts, any comments? All right. Now, at a very high level, we can classify or categorize the problems in AI safety under these three different classes. Those that arise from a specification. What does that mean? Well, this class means we want our agents to behave according to the intentions of the user, the designer of the AI. Then there's a robustness class. we want our AI to withstand perturbations like those adversarial examples. And then there is the third class called assurance, which focuses on analyzing and monitoring activity, detecting failures when they occur, and a little bit of post-mortem analysis, figuring out what went wrong that resulted in a major failure in an AI system. From a technical point of view, you can think of the formulation of the RL problem, this, as a representative sample of all problems in AI. How? Well, in RL, what we want to do is to maximize for an objective. We don't always know what that reward function or the objective is going to look like, so we are going to rely on our experience, our past knowledge. This is where the expectation operator comes in to get an idea of what's going to happen in the future, and we want to maximize for things that can happen in the long run. How is this a representative example of AI? Well, think about the problem of supervised learning, the problem that we spent a couple of weeks studying in the machine learning section of our course. We are looking for parameters, model parameters, W or theta, that maximize probability, a log likelihood probability. Instead of order, we have log likelihood. This general formulation is a good representative of almost all problems that we deal with in AI. And it seems straightforward enough, right? It's very straightforward. We want to find the argument that maximizes this expected sum of rewards over time. But here's the thing. This straightforward equation is actually not as straightforward as it seems. Its building blocks are each a potential cause of major failures. Let's look at the reward function itself. Where does it come from? So in our RL lectures, we assume that this reward function is given to us. There is a reward fairy that generates a reward signal, or the environment automatically creates a signal that we can use as our reward signal. For example, in games, we can use the score as a reward signal. But in the real world, this reward signal is not explicit. Sometimes we have to design it ourselves. For example, for self-driving cars, what should be this reward signal? Is it how close we are to to the goal, to the destination? If so, well, let's look at a particular example. Imagine that you call an Uber and a self-driving car shows up. You tell that self-driving car that you want to get from where you are, let's assume it's in West Haven, to JFK in New York. You have a flight and you need to get there within an hour. So the self-driving car may optimize for minimizing the amount of time that it takes to get you from where you are to where you need to be. And if that's the objective function, the self-driving Uber may actually get you from West Haven to JFK in an hour or even under an hour. But by the time you get there, there will be Navy helicopters hovering over your head, or there may be SWAT cars following you. There are sirens flashing around you. Why? Because the self-driving car has bumped into multiple vehicles on the road, has driven through a mall, has destroyed multiple buildings, may have run over multiple pedestrians. People have died in your way on your way to the airport. Why did that happen? Because you did not explicitly mention in this reward function that you do not want the self-driving car to collide with any other objects or go out of the traditional road, or you did not say, hey, try to avoid hitting any pedestrians. So if you do not correctly specify what you want, the objectives, the values of your agent are going to be misaligned with your values as the user. This is called the alignment problem that falls under the class of specification issues in AI. What's the next component? It's this expectation here. This expectation is over data available to you. What if the data that's available to you, be it experiences of an RL agent collected through the exploration exploitation process, or data collected through data curation for a training data set and such, what if those samples are not representative of the true distribution of data or the true dynamics of the environment? In those cases, this expectation is not going to be very accurate, or it's not going to be very generalizable, and it may give rise to issues in robustness. For example, adversarial examples may have been caused because your expectation is calculated over data points that are not very representative of the true distribution. And then this argmax here itself is another source of issues. The optimization, the approximation may not be accurate enough. It may fall into local optima. It may have errors that cause certain problems in the long run, and this falls under the class of assurance problems. Now, let's dive into the first class, a specification, and look at an example of how things can go wrong. So this is a deep RL agent trained to win this boat racing game. The objective, the reward function, is given to be the same as the score. You can see that this agent has learned to go in circles at this particular location and keep eating those reward blocks, those green reward blocks that are appearing there. What's the problem with this? Well, now the boat, the agent, is not making any progress in the racetrack. So all it's doing is eating these green or blue reward blocks, increasing the score, but it's not moving forward. This is a very good example of specification issues, particularly with regards to the reward problem. Here's another example. So the idea here is to create different blocks and train RL agents or evolutionary policies for moving from one point to the other. And you can see what creative solutions they come up with. A major jump to get from one point to the other, another major jump to get from one point to the other. These are surprising. This is what the authors, Lehman and others, dubbed or labeled these observations, the surprising creativity of digital evolution. What it's referring to is that you don't always know what policies or trajectories your RL agents or evolutionary algorithms are going to find in complex scenarios. It may actually surprise you. And this may give rise to issues like that self-driving car problem that we just talked about, or the boating problem that we just talked about. Now, Victoria Krakovna, who used to be at the Future of Life Institute, I don't know where she is now, I think she may be at DeepMind, has been collecting instances of issues that arise from gaming the specification of the reward function, agents abusing the specification of the reward function to gain rewards while not achieving the objective that was intended by the user. And you can find a summary or a spreadsheet of those instances of a spreadsheet specification gaming in this URL. I don't know whether it's still being maintained or not. I know my friend and colleague Roman Yampolsky has just started curating a similar list, which I'll share with you afterwards, but it's worth taking a look at. Now, why did these happen? Well, what did you expect? Your agent is optimizing what you've asked it to optimize for, right? Here's another example. The problem of asking an agent to fetch some coffee for you. What does it mean? What does the instruction fetch some coffee mean? Do you want the robot to fetch you some coffee regardless of the consequences? For example, can it just kill anyone who's on its way between where it is now and the coffee house? Or if it gets to, for example, Starbucks and the line is too long, should it set the place on fire so that other people get out and the robot can just jump to the head of the line, top of the line, or similar? Well, not really. Uh, one interpretation of this instruction is if everything in the world is the same, and the only difference is whether you have a cup of coffee in your hand or not, the universe where you have a cup of coffee in your hand is preferred to the universe that you don't have a cup of coffee in your hand. But what about the unintended consequences? What about the consequences of your robot's pursuit of a cup of coffee? What if those consequences are completely undesired or unintended, or have a higher cost than the value of a cup of coffee? So as long as the robot does not change other aspects of the environment that you don't care about, everything is fine. Uncertainty about the value of those other aspects is fine. But what about the cases where you do care about the consequences of those actions? Well, this is what we're going to address today. Now, just a quick review of the standard model for AI. We have an agent. We tell the agent to maximize some function for us. For example, the discounted reward function in RL. And surprise, surprise, the agent is going to do just that, exactly that. But this gives rise to a problem, which is very rightly called the King Midas problem. I don't know if you've heard the story of King Midas, but here it goes. In ancient times, there was a king called Midas who asked a magician to give him a very interesting power. The power of turning everything that he touches into gold. The magician abides, and the king, King Midas, obtains that power. He touches a wooden table, and it turns into gold. He touches a silver spoon, and it turns into gold. Awesome. He got what he wanted, right? But then he gets hungry. The chef brings him roasted chicken, and the king touches the chicken. It turns into gold. He can't eat it anymore. The princess comes in, and the king wants to give her a hug. He touches the princess, and she turns into a golden statue. What's a moral of this story? Be careful what you wish for. It may come true. We need to be very careful about how you specify the objective, or for example, the reward function. Otherwise, things can go horribly wrong. Now, one solution to this class of problems is based on bringing the human in the training loop of these agents. How? Well, this is the problem that we have at hand. We have human behavior, which somehow gives rise to an objective, and that objective is used to train a machine to do something similar to the human behavior. Now, classically, so far, what we've done, the way we've looked at the problem has been like this. the human objective is given, there is an objective fairy that gives us the objective followed by the human, what the human wants. And then we use it to train the machine, the agent. Recent proposals are based on a very interesting observation. We don't always know what our objective is. We don't always know what it is that we want, at least not explicitly. So instead of treating this objective as a given, new approaches are considering human behavior and machine behavior as things that are immediately observable and maybe controllable, and they're treating this human objective as a latent variable, as something that is unknown and can perhaps be inferred from human behavior or can be modeled based on human behavior for use in training better machine behavior. Now, examples of current approaches introduced for this sort of behavior include absolute imitation learning or behavioral cloning. What is this? Well, this is essentially supervised learning. How does this work? For example, in autonomous driving, somebody records what action a human agent performs in any state, and then compiles a data set of states and actions performed in that state by a human agent, and then trains a machine learning model on that data set in the very same way that supervised machine learning models are trained. This may work for particular scenarios. For example, 2 or 3 years ago, NVIDIA published a paper that showed that this may actually work for simple self-driving tasks. But what if the agent encounters scenarios or states that had not been experienced before, or very different from states that were encountered by the human expert, which was recorded? In those cases, behavioral cloning agents are very prone to major failures. And this is why I've classified this under myopic approaches. This row is essentially telling us that these approaches are based on human demonstrations. So what are some non-myopic approaches that utilize demonstrations provided by humans, human experts, to enhance the process? Well, one class of non-myopic approaches is IRL, or inverse reinforcement learning. Inverse reinforcement learning is the problem of finding the objective function, the reward function, from observations of the policy or the behavior. So if IRL can be applied to human behavior, then you can learn and learn the reward function and then use it to train the reward function of a human driver, for example, or a human expert, and then use it to train a reinforcement learning agent. Gale is similar. It's generative adversarial imitation learning. It uses generative adversarial networks to come up with better estimates of what the reward function should look like based on the behavior. Now, the second row is not based on demonstrations, or approaches that are not based on demonstrations of how humans act, but based on some feedback, some explicit feedback provided by the human. These include tamer and coach, which we'll briefly talk about, as well as reinforcement learning from modeled rewards. What's happening here? Well, let's look at this, and we'll look at it in just a moment. But in terms of comparing the performance of these proposals, behavioral cloning and imitation learning can at best do slightly better than the human baseline. Tamer and coach can do much better than the human baselines, but RL from modeled rewards, the thing that we're just going to talk about, can do a lot better than human. It can be verging on superhuman results or behavior. This may be a little surprising to you. 10 years ago, if somebody came along and said, I have an AI agent that is performing at a superhuman level, you would laugh it off. But in the past 5 or 6 years, if you have an AI agent, for example, a deep reinforcement learning agent, that is not performing at a superhuman level, or at least better than the human baseline, nobody is going to look at your solution. They're going to say, hey, it's not doing better than humans. Why are we even discussing it? This is a major shift in the state of the art in the past few years. All right. Now, how does reward modeling work? Reward modeling is this approach down here. Here's the general framework for reward modeling. Instead of having an explicit function in the environment that generates the reward, the agent performs an action based on the observation of the environment, and then different trajectories are generated based on different actions that the agent can perform, based on different policies that the agent can have. And then a user looks at these different trajectories and provides some feedback, whether the trajectory is good or bad, or whether a trajectory is better, one trajectory is better than the other. And that feedback is then used in conjunction with the observation of the environment to learn a reward model. So this is a machine learning process. A reward model is learned to reflect both the human feedback and the observation of the environment, which then produces a reward signal that the agent can use to move forward. How does this help in practice? Well, in autonomous driving and developing autonomous driving policies based on reinforcement learning, a major problem is that of ethical decision making. For example, in case the vehicle falls into what we call an inevitable collision state, how should it decide between different items that it can collide with? This actually resembles a classical problem in ethics called the trolley problem. What is the trolley problem? Well, let's look at an excerpt of an episode of The Good Place, which can explain it very well. Let me enable sound sharing, and here we go.
You know, maybe there's a more concrete approach. Here, let's try this.
Oh, God! Michael, what did you do?
I made the trolley problem real so we could see how the ethics would actually play out. There are 5 workers on this track and 1 over there. Here are the levers to switch the tracks. Make a choice.
The thing is, I mean, ethically speaking...
No time, dude! Make a decision!
Well, it's tricky. I mean, on the one hand, if you ascribe to a purely utilitarian worldview...
Okay. So, what did we learn? Chidi? Talk it out, buddy. What are we thinking?
He thinks he just killed a bunch of people with a trolley.
It's just a simulation. I would never make you kill real people.
Oh, well, that's reassuring, because some of the parts of the fake people flow into my mouth!
Michael, can we just go back to the classroom?
We never left. Here, I'll show you.
Look, see, buddy? None of this was real.
Well, they're fake people, but their pain is real. Does that make sense? There have to be stakes, or it's just another thought experiment.
This is awful.
You specifically asked me if there was a way I could connect with the material more. I'm trying, you guys.
Sorry. You're right. I want to help you understand this.
Thank you, Chidi. So, let's try again.
Oh, I thought maybe we would have a discussion.
No, the whole point is to play out the scenario in real time.
Quick, Judy, what's your decision?
Okay, I can do this. I am choosing to switch tracks, so that way I only kill 1 person.
Oh, forgot to tell you, this is the scenario where you actually know one of the people. It's your friend Henry there.
Chidi! How are you, mate?
Henry, move!
Oh, nice trolley.
Out of the way!
I can't, Chidi. My boots are stuck in the tracks.
Henry, move!
Anyway, long time no see.
All right, I'm sorry if it was too disturbing, but you can see that to extract the human values, especially human ethical values in these sort of tough situations, it's necessary to put the human in these sort of scenarios and to reduce the amount of gore instead of putting them in actual trolley scenarios for ethical decision making in autonomous vehicles. One of the things we did in late 2018, early 2019 was to create an open source simulator that enabled or facilitated the creation of these trolley scenarios so that human experts or human beings could take part in it and tell us how they would react to different scenarios so that we can learn a reward model from their choices and train an RL agent based on that reward function so that it can make more ethically aligned decisions in tough scenarios. Now, how does this happen? In one of the modes of learning rewards from user feedback is what we call the Bradley-Terry model. Two trajectories are shown to a human expert or a user, and the user selects which one is preferred to the other one, which one is better than the other one. And these results are used to optimize the reward function, to adapt the reward function according to the human feedback. And some of the results on typical benchmarks, such as Atari games, show that with a few thousands of labels provided by a human supervisor, the process can be made a lot more efficient and can reach superhuman performance at a much faster time. And of course, it can even do better than vanilla reinforcement learning that is not based on human feedback at all. Another approach is based on combining imitation learning, like behavioral cloning and reward modeling. And one very, very basic sample of this proposal is something called deep Q learning from demonstrations, DQFD. But all of these proposals have a small problem. They are defined for toy scenarios like Atari games, like simple simulation scenarios. How can we scale them up to domains which are too complex for human feedback? It's too complex for even an expert human to provide some feedback on. There are some preliminary proposals on how to tackle these cases. For example, safety via debate by Irving and others is based on an adversarial competition and interaction between two policies, resulting in certain simpler states that can be judged by a human supervisor. So at this point, a human expert can simply decide whether this route is better or this one. Similar proposals include iterated amplification by Paul Cristiano and recursive reward modeling by Leike and others. Now, let us talk a little more about some of the proposals in this domain. One of the problems in, for example, reinforcement learning as an instance of a promising solution towards human-level AI or artificial general intelligence is that of unsafe states. So some states may be undesirable for the agent. They may put the agent on a trajectory that leads to undesirable outcomes. Now, or they may be undesirable overall. For example, if you're playing soccer and you shoot a ball, your agent shoots a ball that ends up going out of the limits of the field, that's an undesired state. You don't want the ball to be on a trajectory of leaving the field. So how can those states be prevented? Well, the idea in this paper by Saunders and others is to essentially have a human observer that can pause the simulation or the scenario in the middle of it annotate particular states as undesirable, and then bring the simulation to one step before the undesirable or undesired state, and then keep the training running while avoiding those states that are marked or annotated as undesired. What about the shutdown problem? You remember the shutdown problem? We have a robot that has become insane. It's terrorizing the neighborhood. We have a Roomba that is trying to vacuum clean your cats, for example, and you want to switch it off. But it's smart and it doesn't allow you to switch it off. Why? Because it's against its optimization its objective of vacuuming everything that's inside. There are some proposals that can help with this. For example, in 2016 and 2017, the idea was proposed to retain uncertainty over the reward functions, as well as switching the values of the reward function. And when the reward value for a particular state becomes negative, then the agent should stop operating. Another solution came out of our lab. This is a paper that I wrote with Dr. William Shu at K-State in early 2019. The idea is to train the RL agent in two different environments. So its policy is responsive to two different sets of tasks. One is the set of tasks that it was originally intended to optimize for. The other is what we call the control environment. It's essentially a set of states that are unlikely to be encountered in the actual original environment. Now, those set of states can include, for example, certain visual configurations, certain visual signs. If a predefined sequence of visual signs are shown to that agent, then the agent's policy is already optimized to stop operating and allow for the off switch to be pressed by the user. Now, there's two more ideas that I want to quickly talk about in the remaining 5 minutes. One is the issue of modeling AI safety problems. AI problems are becoming more complex. AI models like deep reinforcement learning are already too complex that we've invented a new field to understand what they're doing. It's called model interpretability. We can assume that AI and AGI are complex systems, so reducing their complexity and looking at a reductionist model of them may not provide us with much information about emergent faults. What are the current trends in the AI safety community and AI safety research? There's a major focus on safe design. So a lot of the AI safety community, much of the AI safety community is focused on coming up with approaches that enable safe design prior to faults happening. And this includes formal analysis of the control problem, for example, controllability and reachability, which is already too difficult for these complex systems. Also, there are some technical abstractions like looking at the components of the training algorithms, the model architecture, and such, which have already become too complex for realistic analysis of how faults can emerge in AI systems. So there is a need for higher level abstractions. To address this problem, back in 2018, my colleague Roman Yampolsky and I started looking at human cognition as a point of inspiration. It's almost general purpose intelligence. Of course, there are arguments against this. And it's adaptive to dynamic environments, but also it's prone to psychological disorders. What are psychological disorders? There are self-reconfigurations in cognition and behavior that are deleterious to the core and long-term objectives of self or the social ecosystem. It turns out that this is very similar to safety issues in artificial intelligence and artificial general intelligence, which are essentially defined as unintended or emergent behavior that is harmful to the core and long-term objectives of the designer or the society. all right, what can we do with this? For some reason, my slides are locked, so give me a moment to reshare my screen. Here we go. So we proposed a psychopathological framework as a higher level abstraction for modeling of AI safety problems. This framework includes multiple components, including modeling and verification tools inspired by what's already available in human psychopathology, classification and diagnosis of disorders, guidelines and tools for classification and diagnosis of disorders, and high-level guidelines for treatment in quotes. Once again, my slides are locked. This should be the last technical issue. Let me reshare my screen. Here we go. And as a proof of concept, as a demonstration of how this approach, this framework can be used, we investigated the case of reward hacking in reinforcement learning in a simple scenario of the game of Snake, that old game that you might have played with in Nokia phones. But we modified it a little. In Snake, we have the original seed, food seed, and we already have them there. We call them the healthy seeds. They add R to the reward when they are consumed and 1 to the length of the tail of the snake. And we also added a drug seed in red, which adds K times R. K is a positive value to the reward. So it's giving the snake more reward, more instantaneous reward, but it's also adding more to the length of the snake. Why is it bad? Well, the longer the tail is, the more likely it is for the snake to bite its own tail and die, right? Die prematurely. Now, we trained the Q-learning agent and showed that if these conditions are satisfied, the snake learns to behave in an addicted manner. It becomes addicted to the red seed, and it can essentially, it dies a lot sooner than it could have if it had only taken the blue seed. And this is one instance of how the psychopathological framework can be applied to the AI safety problem. This was very popular with the news media. It was covered by Axios, CNET, ABC News, and a few other international news agencies back in the day. Now, in terms of assurance, I know that we're 1 minute over time, but please bear with me for another couple of minutes. Here are a couple of things that we looked into. We looked at the resilience and robustness of deep reinforcement learning. This is essentially what my PhD dissertation was about. And one of the solutions we developed was to fight fire with fire. We proposed an adversarial reinforcement learning agent whose objective is to cause the maximum amount of disruption and loss in a reinforcement learning agent that we want to analyze or measure its resilience and robustness. And this approach was demonstrated in various cases, including the feasibility of this approach was demonstrated in various cases, including autonomous navigation policies and industrial smart grid control policies based on deep reinforcement learning. And this is the final topic that I want to bring up, and it's the need for a post-mortem analysis or autopsy. We know that failures in AI are inevitable. Now, here's a problem. When a failure occurs, we want to figure out what sequence of events led to the failure. We might need it for technical analysis, for example, figuring out what the sequence was so that we can prevent or mitigate the repetition of the same issue by debugging, or it can be for legal aspects in response to legal requirements. We want to figure out who's liable for a failure that has occurred. We want to figure out who's responsible for the failure, or we want to figure out whether the fault was intentional or not, whether there are criminal intents behind the harm that was caused based on the failure. To address this, Professor Beguli and I proposed the founding of the domain of AI forensics. What's the definition of AI forensics? Scientific and legal tools, techniques, and protocols for the extraction, collection, analysis, and reporting of digital evidence pertaining to failures in AI-enabled systems. What's the general scope? Well, we want to figure out what were the sequence of events and conditions that led to the failure. Did the failure result from malicious actions? Which party or parties are responsible for the failure? Would it have been possible to prevent the failure? Or where, in other words, at which stage or component did the failures take place? And we came up with this general taxonomy or landscape of subdomains or directions under AI forensics. If you're interested, you can read our paper. It was published earlier this year at AI Safety Workshop, and it's available in our websites, both Dr. Beguli's website and myself. Now, what are some of the ongoing areas of research? There are numerous areas of ongoing research. AI safety is a super young and super significant area of research, but unfortunately there aren't enough people working on AI safety problems. They are more interested in getting the thing to work, not making sure that in the long run, the thing that they've made is not going to end up killing everyone or causing the end of human civilization. Some of these include when we incorporate human input in the training process. What if the humans make mistake? What if the input is imperfect or noisy? Or what if we have multiple humans? Other instances include safe exploration, coming up with better strategies for multi-agent artificial intelligence settings where certain interactions between the agents may result in emergent deleterious patterns of behavior or cultures of behavior and such. And these are some of the areas that my lab and a few other research labs, including one at UC Berkeley, one at Oxford, one at Stanford, and another at Carnegie Mellon, are looking at. So if you're interested in learning more about these, do come and talk to me or talk to one of my students in the lab. We are all working on questions and problems related to AI safety and security. I will also provide more optional resources, including a couple of my own recorded lectures on tangential and relevant topics in AI safety, as well as some papers and reading material that can supplement this general study. I'm sorry I went so fast. This was a lot of material to cover in the short time that we had. Now, this is a good time for you to ask any questions you might have. No questions?